Hello everyone, welcome to a series of videos on mathematics behind machine learning and artificial intelligence as indicated by the screenshot right here. We're going to begin with vector spaces. This is a formal presentation, not as rigorous as a textbook, sort of like a middle ground between a mathematical textbook and a sort of an informal way of describing things. So most of the things, if you're able to just read these things on your own, you'll pretty much understand most of the things. But I think somebody narrating it, somebody making people understand, along with the written notes, would go a long way. So basically, we're talking of basic notion of vector spaces. The way we begin this notion is by trying to understand R2. Okay, so it's a R2 space. You have a point x1, x2, x1 and x2 both belong to both are part of real line. Okay, so now what we want to prove is a bunch of properties that are part that will eventually, when we generalize it to R3 and Rn, will equate to vector spaces as definition. So we take R2, which is the notion that we are familiar with, two-dimensional real space, and then we take a look at some of the properties. So one of the first properties that we look at is additivity. You can add a couple of vectors and see that the sum that is added here is also part of the vector. So that basically satisfies additivity. You also want to find out commutative property. So you want to find out if x plus x2 and x2 plus x1 are both the same. If a vector is enlarged or contracted, meaning the scaling property, wherein you have something called alpha, so it's described here. So alpha will belong to a real line. So this is a scalar quantity. This is the scalar multiplication of the vector. The scalar multiplication of the vector also is part of R2, as a result of which even scalar multiplication is valid under vector spaces. Then you want to find out the additive identity, zero vector space, or zero vector. Let's say zero vector is part of R2 as indicated here. This, along with the definition that vector addition, it is easy to see that zero vector is an additive identity. Adding any vector to it basically doesn't change the value of the vector. Now once you're through with that, as you can see, now we try to prove all the properties that we did prove for R2 for R3, right? So basically additivity, you can add a couple of vectors, and the sum of vectors in R3 space is still part of R3. Okay, my handwriting is a little off, but I think it'll get better to get used to the high resolution of this pen. The note, the plus here is not quite is quite different from the plus in case of R2. While the defining vector space, it is crucial to define plus that makes the space of a vector space. That makes the space a vector space. I will. Okay, there's some exercise that people can probably do. Now we generalize to the fact that there is an Rn space, indicated here. I won't write something that's already there on the screen, so I hope you can just read through. Now, the whole notion of defining a vector space is look at something that you can already understand. So most people are familiar with two-dimensional spaces, so we took R2 as the initial case. We generalized that to R3 and proved all those properties. Assuming that is all proved, and all the properties that we defined, additivity, commutativity, identity, additive identity, all of them hold true for R3. We take a look at Rn, and there aren't any reasons to believe that all these properties hold good for Rn as well. So basically, any real space is a vector space. Okay, so having understood, having seen the general abstraction for Rn, now we're in a position to define what a vector space is. So definition is right here. I should be a little careful as to how I go about doing this. Vector space A is said to be a vector space over R if there exists maps, the plus V cross V cross map from V cross V to R. V cross V to R is defined by x plus y, and the multiplication is basically a scalar multiplication. You have a mapping from a real value cross product of a vector that is mapped to a real number. So basically a vector space follows all these properties. So these properties haven't been numbered, but you can probably list them. 1, 2, 3, 4, 5, 6, 7. So all these 7 properties make up a vector space. So basically, if you take 2 points that belong to vector space V, the addition of these 2 vectors also belong to vector space V. So 0 is a additive identity. If you add any vector to 0 vector, you get the same value of the vector. So that is one. Second is you equate associative addition to 0. That would equate even on the RHS. There is additive associativity, which is 0.4. 5 is scalar multiplication of the sum of vectors. XY belong, okay, I'm talking about this right here. Okay, and so the scalar is the associativity holds, and if you multiply any vector with x, you will get the same value. It's also true if you have associativity property with respect to scalars, alpha, beta. Multiplied with x is equal to alpha. I was like, what the hell? Let me write it. So that being the case, we'll just move to the next section of it. So having seen how vector spaces are defined on a general context, having seen it move from R2 to R3 to Rn, and now we define the vector space in a very general context, we can take an example and explore as to what the geometric view is. I think these are some of the fundamentals. I mean, you might as well read it. I'll just give it a couple of seconds. If you're interested in reading it, you can probably go ahead and do it. We'll just get to some of the definitions in the meanwhile. So one of the definitions is the definition of linear combination. I mean, there is a reason this needs to be highlighted. Yeah. What exactly is a linear combination? Assume that x1, x2, xn is a set of vectors in a vector space V over R. Now, assume that all let alpha I, which is a scalar number going from I to n, I from 1 to n. Then the vector x1, alpha 1, x1, alpha 2, x2, dot alpha n xn belongs to vector space V. It's called a linear combination of vectors. Basically, if there is a scalar multiplication of each vector, that is the linear combination. Another interesting fact about the standard vectors is you can write even E1, E2, these are standard vectors, right? It's indicated here. You can multiply each one of these as you can see, honking is not a thing of the past. People still honk even though I'm making videos here. It's okay. The inconvenience is sort of pardoned. As hard as it might be, we don't have a choice, so we might as well move on. Okay, geometrically it means no more than two vectors lie in the plane. Now, this is something that you can think about, as to why this is the case, as to why this being true, why this is the case. So having understood that, let's move to the next definition of linear independence. I mean, you have scalar multiplication of scalar with a vector, then you if the linear decomposition of a scalar with a vector equates to 0, this is the condition for linear independence. So here alpha is again defined from alpha I is a point on a number line or a real line where I takes the value from 1 to n. This implies, for this to be true, for this notion to be true, I don't know why there's latency in how I write. For this notion to be true, all alphas have to be 0. Okay, that's the only way it can be independent. So the standard vectors have another interesting property. Apart from this definitional attribute, we have another interesting property wherein you can write a component of a vector in terms of standard basis. So this is basically E1, E2 and En. So you can write it as x1 E1, x2 E2, x and En. So that is possible. So once having understood that, we can probably proceed and there is a definition here. Assume that x1 x2 xn in a vector space V over R spans the vector space V. If for all x, I'm reading here, if for all x belongs to V, there exists alpha I that belongs to R, where I takes the value from 1 to n, such that x is just a linear combination of all scalar alphas with corresponding components of xn. Now, okay, let's move to the exercise. I mean, the exercise is pretty simple. Assuming that you have a set of vectors which span the vector space, you add something to this list which also spans the vector space V for all x belongs to V. The above exercise, what it basically means is there are some set of vectors x1 to xn which span the vector space. If you add another vector to this set of vectors which also spans the vector space, we can basically say that spanning set is not unique. I mean, there can be more than one spanning set, which is indicated here. The above exercise indicates that there could be redundancies, very important, in spanning set of vectors. This, however, can be removed one by one until we get spanning set from which removing even a single vector from it will make the set lose the property of spanning set. If you want to lose the property of spanning set, basically you will have, let's say there are n vectors which span the entire vector space, and you remove one, you don't span the vector space anymore. That's what it's talking about. So there can be redundancies in spanning set of vectors. That's the point, which is indicated in line 1 and 2. Okay, line 1 and 2 here. Okay, now having understood that, we'll have a notion of what a dimension is right now. Set x1 to xn is called the basis of a vector. I think I have let's continue this in another lecture.